Okay, good. So does it make a sound if there's no one here there to hear it? Yes, it does. And the reason is, what are sound waves? Like if we think about what a sound wave actually is, so it's a vibration of particles. So when a tree falls, is it still vibrating particles? Yeah. Okay, so there's still a vibration of particles. Okay, and is it going to create a wave? Yeah, it'll still create a wave. Okay, it'll still travel through a medium. It'll still have a frequency. So it's still a wave through a medium. With some frequency. Okay, so that hasn't changed. So if you're not there to hear it, it still does those things. So it's still going to make a sound. Sound is not dependent upon you hearing it. Okay? If the entire world went deaf, would sound cease to exist? No, because you can still feel the vibrations of sound. Okay? So the sound still exists regardless of whether you can hear it or not. Yeah, I'll zoom in a little bit more so you can see better. Okay? So regardless, you're still going to hear a sound because it's still going to do these two things. Still going to vibrate particles, still going to travel through a medium with a frequency. Good. All right. For the Alien fans out there, and if you haven't seen that movie, then unless you don't like scary movies, then you should watch it. It's awesome. Okay? In space, no one can hear you scream.
Because there's no medium for the sound to travel through?
Bingo. There is no medium for the sound to travel through. So no medium. For sound to travel through. Which is why it's a great tagline for that movie, because it's true and it's also true. Okay, so no medium for the sound to travel through, so if you were to scream, no one would hear you, because you're not going to do anything. I made this point out before. You can see the sun, but you can't hear the sun. Okay, you can't hear the sun because sound doesn't travel through space. We'll get to why you can see the sun.
No, I forgot. That's a good question.
Good talk. All right, 3. So why does the tuning fork have its own unique frequency? Why does it always play the sound when it's hit? So let's start with, why does each tuning fork have its own frequency? So each of these tuning forks is different. Why is it that they have different frequencies? Kind of spoiled this one. Someone can feel confident. Nate, you got this one. Why are they different? Why are the frequencies different? So when I played this one 250, this one 1,000, why are they different? Bingo. The way, like their shape, what they're made of, their size, their shape, like all that stuff. So they're all have different, I'll just generalize it here and say physical properties. So what metal is it made out of? What shape is it made into? How long is it? How short is it? How well does it bend? How large of a U shape is it? Like all that stuff affects the physical properties, and all that stuff affects what the actual frequency is going to be. So if they're all different and they all have different frequencies, then why is it that each one has its own set frequency? In other words, why is it that the 1,000 is always 1,000? It's never anything different. Why?
Because the size and shape aren't changing?
Because its individual size and shape are constant. Yes. So the reason why is because each has its own natural frequency. caused by its own properties. So it's not changing. Because it's not changing, it's going to be consistent in what sound it makes. So that sound is the same every time I hit it. And the reason is I'm hitting it roughly in the same place every time, and it's the same object. So it vibrates at a very particular sound. Right? Like whatever you hit, it vibrates at a specific frequency. And the reason is it's a specific object in a specific shape with a specific material, and so it vibrates at a set frequency. That frequency is called the natural frequency. So let's talk about resonance. So we defined resonance last time, and the way we defined it was resonance is when an object is forced to vibrate at its natural frequency it does so with a large amplitude. And that just means loudly. So, when an object is forced to vibrate at its natural frequency, it will vibrate at that frequency with a large amplitude, which is just a fancy word for saying loud. It will vibrate really loud. And that's just because of it vibrating at that frequency it wants to already. Okay? So let's look at a couple examples of this. All right, first one here. I have a tube. It's got a frequency of 880 hertz. I got a tuning fork. It's got a frequency of 880 hertz. So, if I use the tuning fork to make the tube vibrate, it should vibrate at that frequency, and it should do so with a large amplitude. Hear that change? That's resonance. I'm forcing the tube to vibrate at the frequency it wants to, and so it does so loudly. Ooh, that was a good one. Now, it's not just anything. So here's 1,000, and it doesn't do it. Doesn't do it at 1,000, because that's not the right frequency. It's vibrating, but it's not going to vibrate loudly. So if I play 1,000 and hold it up to it and take it away, I can hear a really dim 880 hertz because it is vibrating, but it's not vibrating a lot. That's the key. Okay? So for this one, explain the tuning fork demo, what it has to do with resonance. So when the 880 hertz fork forces the 880 hertz tube to vibrate, it resonates. They're doing beats next door. It's not annoying at all.
Wait, what if the tuning fork is made out of two different metals on each side?
It would change the frequency, but it would still have a frequency.
It'd be the same.
No, like if I made this one out of two different metals, it wouldn't be 1,000 anymore. Okay, let's look at one more example. I want to look at a visible example that you guys can see. So basically what happened was wind forced the bridge to vibrate at its natural frequency. It's kind of hard to read. So the wind forced the bridge to vibrate at its natural frequency.
So the wind was strong enough to do that?
Mm-hmm. Well, it wasn't even that strong. They just built the bridge unluckily. Like, it just happened to be the exact right distance that speed in that direction would do it. Now, this was in Seattle, so, like, there's a lot of wind in that area anyway. So, and its natural frequency. So, it resonated.
Well, that didn't do it modern day bridges do that?
No, because they've designed them better now. Like, they don't make them so long. They break them up into sections so that they don't resonate and that sort of thing. There were some other factors too, but that's kind of the big one there. Okay, so I wanted to show you what resonance is. So now what we're going to do is we're going to watch a little bit of a video of this. So